Today we are going to talk about another way to test convergence or divergence of series. And these are specifically series that just don't fit any other type and they can't be integrated. Integral test was yesterday. That was when the series integrated nicely. It was a great U substitution. But if it's going to turn into an integration by parts or something like that, that's the last thing you want to do is integrate it. So we're going to talk about how we can do the determination of convergence or divergence without having to integrate it. And it's called comparison of series, and actually it's two different methods. So we're going to start by looking at what it says right here. In order to use the convergence test we've studied so far, the terms have to be fairly simple. This is supposed to say simple. You fix that. And it had to be in an exact form. Any deviation, however slight, means that the convergence test can no longer be used, and it could make a difference as to what happens. For example, this one right here, n over n squared plus 1, doesn't pass the nth term test, but if it's cubed, it does. Or actually, yeah, this one does not fail the nth term test, so this one diverges. This one's a p series, 1 over n squared, but 1 over n squared plus n is not, so you can't use the p series test on this. This is a geometric series, but this one is not. This one can be nicely integrated, but this one can't. So we've got to come up with something that will work on those the weirdos, basically. What works on the weird series? What can we do? Now, the method we're going to use is we're going to compare an unknown series, the problem, with a series that we know, something that we know what it does. And we're going to use that comparison to figure out what's going on. So do me a favor, put a big box around these 4 series right here. Put a big box around it, because this is important. We're going to actually transfer this into the flip chart later. These are the 4 what we call benchmarks. They are the comparers. We're going to compare to one of these 4 based on the way our problem looks. Now we can also modify these a little bit, and we'll talk about that as we go. So one of the ones we can compare to is the divergent harmonic series. So go ahead and underline whether it converges or diverges as well. So the harmonic, remember, diverges. Some p series converge and some diverge. The one on the right is a convergent p series because p is greater than 1. That's why it converges. The divergent p series is when p is less than 1. Oh, I forgot to close my parentheses. And then the convergent geometric series is when you have a times r to the n, but r has to be less than 1. Well, in reality, r has to be between 0 and 1. Let's put that down there. 0 is less than r is less than 1. That's a more accurate statement. Okay. When we learned geometric, we said that r had to be between -1 and 1. But for these specific problems, they have to be positive. So you'll never have a negative r. You don't want an alternating series. Actually, alternating series we're doing tomorrow. That's the next one in the process. Okay? So the first test we're going to learn is what's called the direct comparison test. We're going to directly compare our problem to something that we don't know. Okay? Now, this one makes more sense if you draw it out. So we have 2 series, A and B, and it doesn't matter which one is the one we know and which one is the one we don't know, as long as one is always less than the other. Notice that they're both positive here. A is between 0 and B for all of the n's in question. So this one says if B converges, then A is going to converge. Okay? So draw me a first quadrant, just a tiny one right here, kind of long on the x-axis. And we're going to plot the series as like a continuous graph. Okay? Now, B is always above A, and B is going to converge. Now, when we drew convergence last time, we drew it a situation where it went down towards 0. Do you remember that? So if you draw a graph that goes down towards 0 and call it B, and A is always less than B, what's A going to do? Converge. It has to converge also. A is always under B, and it's bigger than 0, so A's got to converge also. It's kind of forcing it to converge. It's pushing it down. So if the one is above and it converges, it's going to push the one below it to converge as well. Okay, now look at the next one. Let's draw another one right here. This one says, if A diverges, then so does B. And it's important that it's in this order. Okay? So now I'm going to draw A first, and I want it to diverge, and that would be a situation like going up to infinity. Okay? If A diverges, and B is always on top of A, B also has to go up forever, doesn't it? So B will also have to diverge. So that's something that you're going to have to wrap your brain around. If the one on top converges, then the one underneath it must converge as well. Okay? And if the one on the bottom diverges, the one above it has to diverge as well. So that's what we're going to be doing, is we're going to be comparing it to another series. So let's walk through a couple of these and see how they work. Okay? Determine the convergence or divergence of this. Well, that's not a perfect P series or a perfect anything. Okay? But because it has 2 to the n, I go back up here to look at the 4 that I boxed in. Which one of these 4 has an n for a power? Which one has n as an exponent? Not n as a base. It's the geometric series. Do you see that? The n is the exponent. Okay? Now, this series resembles 1 over 2 to the n, which is a what? That was a convergent series. Okay? Now, this doesn't really look like a times r to the n, but if you write it out a little bit, you're going to see that it is. Now, one of the things we like to do is go ahead, can you see all of this? Yes, you can. And label each one of them A, one of them B, it doesn't matter which is which. So I'm going to call this one A, and I'm going to call this one B. Okay? It doesn't matter which one's which. Now, I want to write out A. Excuse me, I want to write out B first, because they want me to do a term-by-term comparison. I'm going to come back to this Y in just a minute. So, for n equals 0 to infinity of 1 over 2 to the n, do me a favor, let's write out the first 4 terms. If I plug in 0 for n, what do I get? 1. If I plug in 1 for n, I'm going to get 1 over 2, right? What about 2 for n? What's it going to be? 1 over 4. What about 3 for n? 1 over 8 plus ... What am I doing every time to get from one term to the next? Multiplying by not 1/2. You're multiplying the whole fraction by 1/2. Do you agree with that statement? So this is a geometric series with r equal to 1/2. Do you see what I'm saying? And that's the y. It's a geometric series and r equals 1/2. That's why it converges. Okay. Now, let's take the one that we want to know about. This is B of n. This was B of n. Let me write that down here. A of n is going to be, now I'm not going to copy the series. Oh, let me go ahead and copy the series again. N equals 0 to infinity of 1 over 3 plus 2 to the n. Now let's carefully plug this in term by term. 0 first. This fraction will be 1 over what? 2 to the 0 is 1 plus 3, so this is 1 over 4. If I plug in 1, what am I going to get? 1 over 5. Then 1 over 2 squared is 4. Plus 3 is 7, and then 1 over, this is kind of weird, 2 to the third is 8 plus 3 is 11. Now that doesn't look like any sort of pattern that you've ever seen, but that doesn't matter. What matters is, is 1 always bigger than the other? So look at it term by term. Is 1 always bigger than 1/4? 1/2? 1/5? Yes. Is this one bigger than this one? This one bigger than this one? Is it going to continue to be that way? Yes. So the conclusion is that B sub n is greater than a sub n for all the n's. Yes?
You always do B first?
It doesn't matter which one. You label one A and one B, and then you do the one that you can do quickly first, the one that's easy to do. Okay? Now, B converges. B converges. So if B's on top and B converges, what's A going to do?
Converge.
It's going to converge also. Okay? B is greater than A, therefore A sub n converges by the direct comparison test. A converges by the direct comparison test. Now, you must write that B is greater than A, or that B is less than A, depending on the scenario. You have to write that sentence down, because I know that this one converges, and since this one's always on top of that one's got to converge too. Yes, sir?
Is this sort of similar to the squeeze theorem?
Yes, it's very similar to the squeeze theorem. It's very similar to the squeeze theorem. I am squeezing it down to convergence, or letting it blow up to divergence. Okay, any questions on this problem? All right, let's go to the back. So turn to the back of the paper. So we have this other series. It is 1 to infinity of 1 over 4 plus the square root of n. Well, it doesn't fit anything because of that 4. Anytime they add numbers on the bottom, it messes everything up. But we're going to say, oh, that kind of looks like this one, 1 over the square root of n. Now flip back to the front and see, is that one converge or diverge? 1 over the square root of n. It says it diverges, right? Which is divergent. Now, what kind of series does it say that it is? It's a P series, and P is less than 1. That's how you know it diverges. P series, P is less than 1. Okay? Now, let's see if this one, now where do we want this one to be? If it diverges, do we want it under the other one or over the other one?
Under.
We want it under, because if we want to make something go up, we want the other one underneath it. Does that make sense? Okay, so if this one on top is divergent, do we know what the bottom one does? It could do either thing, couldn't it? It could go up and diverge too, or it could go down. I don't know. So if I want divergence, and it has to be the bottom one diverges to bring the top one up as well. So let's see what happens. So let's call this one A of n. Let's call this one B of n, because we don't know who's on top. So we're going to say that B of n, which is 1 over the square root of n, I'm just going to write down the A sub n term. Let's write out a few terms here. So this would be 1 over, what are we supposed to plug in first?
0. Wait, oh, wait, 1.
It's got to start at 1. Can't plug in 0. Well, that'd be a problem. 1 over 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4 plus dot, dot, dot. Y'all agree with that statement? You don't need to clean it up. A of n is 1 over 4 plus the square root of n. So that's 1 over, plugging in 1, that's going to be 5, right? And then 1 over 4 plus the square root of 2. You with me?
Numbers.
Yes?
How come sometimes you start with 0 and sometimes you start with 1?
It doesn't matter, but in this case, if I started with 0, I'd have a big problem because I can't have 0 on the bottom of a fraction. It just depends on the series itself.
But it doesn't matter if you start with 0 or 1?
Depending on how the series is written, sometimes it does, but the same series can be written 2 different ways sometimes. Sometimes starting with 0, sometimes starting with 1. It would have to just change the n equation a little bit. Okay? But the point is, because we're looking at infinity, so it really doesn't matter what happens at the beginning, except it's got to be there. So the next term would be 4 plus the square root of 3, 1 plus 4 plus the square root of 4. Okay. Now, who's bigger? Okay. B is bigger, right? Term by term, every time? Remember, bigger denominators equal smaller fractions. right? You agree with that statement? Bigger denominators equal smaller fractions. Why doesn't this comparison help? Because B is bigger than A. B of n is bigger than A of n. Why doesn't that help?
Because
Is it because they do
then
different things? They do different things?
They do, it's not that they do different things, it's I don't know what the other one does.
you need, if it's diverging, you have to know what A is doing, right? Because B's on top.
Because B's on top, B diverging doesn't tell me anything, because A could go anywhere in underneath it. Does that make sense?
Yeah.
B could be, I mean, A could be anywhere. Since B diverges, we cannot conclude, oops, misspelling, conclude what A does. What A sub n does. B sub n, let's be a little more formal here. Since B sub n diverges, we can't conclude what A sub n does. It could go anywhere. So that didn't help. Sometimes tests fail. Is there anything you've ever done in life where you tried something you thought was going to work and it didn't work?
Mm-hmm.
Yes. Okay. Life happens that way. So does math sometime. Okay, now they said, you know what, let's try 1 over n. That sounds like a strange one to try. Well, first of all, what does 1 over n do? Converges or diverges? Go look on the front if you don't remember.
Oh wait, convergence.
Oh wait.
Go look. It diverges. What kind of series is 1 over n? Do you remember the name of it? It has a special name.
Harmonic.
It is the harmonic. Very good. Harmonics diverge. And we're going to call this one A of n now. Excuse me, B of n. We want it to be the, A of n is the original, B of n is what I'm comparing it to. So B of n this time, which is 1 over n, is going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot, dot, dot.
Wait, why did you say it has to be B of n?
Because I've already called the original problem A of n. Okay? Now, that one still looks to be bigger than the other one, so it doesn't seem to help. But it actually does, because eventually, because of the way harmonics work, the harmonic is going to end up being smaller than the other one. Okay? Now what they do is they walk you through this. It's to show by graph that x will eventually be bigger than 4 plus the square root of x. So over here, draw a first quadrant. You got plenty of room. What does the graph of y equals x look like? Straight line at what angle? 45-degree angle. Looks like that, something like that. That's x. Okay. What does the square root of x look like? Kind of looks like this. I call it the fountain graph. Like you hold your water in a fountain that way. I don't know. Okay, what does the 4 do to the graph? Up 4. So 1, 2, 3, 4. If I draw that thing like that, what's going to happen? It's going to cross the x and then eventually be on the bottom. Do you agree with that?
Yeah.
So at the beginning, x is bigger. That's what we noticed here. But then eventually it's going to switch. I mean, x is smaller. I said that backwards. I'm sorry. So what can be concluded? If x will eventually be bigger than 4 plus x. X is going to be on top, right? So if x is bigger than 4 plus the square root of x eventually, what happens to the fractions? Bigger denominators mean what kind of fractions? Smaller. So if this is true eventually, this is true eventually also. So now 1 over x is now under the other one, and if it diverges, it's pushing the other function to divergence as well. Okay? So basically we can say since b of n is greater than a of n, eventually Did I say that backwards? I think I just did. B of n is less than A of n. I did say it backwards. Rats. Because that's what I wrote right here. This is B, this is A. B of n is less than A of n eventually, then A of n diverges by the direct comparison test. Since B of n, sorry about that, I didn't realize I was down so low. Since B of n is less than A of n eventually, and B of n diverges, then A of n also has to diverge eventually by the direct comparison test. Now you're probably thinking to yourself, Ms. Bell, I would have never thought of that. Would never have gone down that road. I know, okay? So pretty much every math book will tell you that of the two comparison tests, this is the one that is the last resort, okay? The one I'm about to show you is much cleaner and much better. So I'm going to show you that this other comparison test works so much better on both these problems, okay? So you don't really have to worry about this. And the reason I do this hard stuff is to show you how much better the easy stuff is. Does that make sense? Okay. So now we're going to go to the better test. It says so right here. There's a better test, and it's called the limit comparison test. If you can take a limit, this one's better, okay? And I think you can. Put a big star by this one right here. Here's the rule for this one as well. Okay. So we have our function that we're given, A of n. We're going to compare it to another function, B of n. And then what we're going to do is we're going to take the limit as n approaches infinity of the quotient of those two. If we can get a number answer, i.e. not infinity, then both of the series will do the same thing. So if you happen to pick a divergent one, and my limit gives me a number, the other one will diverge. And if I happen to pick a convergent one, the other one would converge. Okay? So let me show you. These four right here are the same four benchmarks. These are the same four ones that we recommend that you use to compare to. They're the same as before. And we're going to put them on the flip chart so that you have them to see when you use the flip chart. Okay? So 1 over n squared, 1 over the square root of n, or a geometric. All right? So let's go to the next page. And what this is doing is it's doing both of the same problems we just did, but we're going to do it with limits. Let me show you how this works. Now, they start out telling you which ones to use. Eventually, you're going to have to choose for yourself, and I'll talk about how to do that. Okay? So here's our first problem. We'll call this A of n. We'll call what we're comparing it to B of n. And this one converges. They tell you that already. Okay? Now when you do your limit, as n approaches infinity, you're going to draw a giant parentheses because you're going to make a big fraction. It's going to be a fraction over a fraction. Now, does it matter which one you put on top? Honestly, it really doesn't in the long run, but putting it a certain way will make the problem go faster. And you want your simplest fraction on the top. Your simplest fraction. So which one's the simplest fraction? A of n or B of n? B of n. So we're going to put B of n on top. So please put 1 over 2 to the n over 1 over 3 plus 2 to the n. Like so. You want your simplest one on top. Okay? You'll see why in a minute. When you have a fraction over a fraction, how do you simplify it?
Reciprocal, just change the letters.
Reciprocal of which one?
The denominator.
The bottom one. So we're going to flip the bottom one up. So that would be the limit as n approaches infinity. Now I'm going to go ahead and write it out here. 3 plus 2 to the n over 1. I should have squeezed that in beforehand. So I flipped it up. So now the denominator of the second fraction becomes the numerator of the first fraction, right? Of my answer. So this is now going to be 3 plus 2 to the n over 2 to the n. Now I think you can see why I did this. I wanted the simpler fraction on top because now I can break that into two separate fractions and make it a lot cleaner and easier to solve. Okay, so what I'm going to do is come down here and say this equals the limit as n approaches infinity of 3 over 2 to the n plus what? 1. 2 to the n over 2 to the n is 1. Okay? As I put an infinity in this exponent right here, what is this fraction going to become? 0. So this is going to 0. So 0 plus 1 is 1. All I care about is that I get a number answer. I don't care what it is. As long as it's a number, I'm good. A positive number, actually, is what it needs. Since I got a positive number, I can now say, therefore, A of n converges by the limit comparison test. A of n converges by the limit comparison test. That wasn't so bad, was it? Not really. Okay, the next one is the one that was really ugly a minute ago. We tried something, it didn't work, so we tried something else. The something that we tried at first that didn't work works beautifully with the limit comparison test. Okay, here's my problem. This is A of n. Here's my comparer. This is B of n. And it diverges. Now, we don't care who's on top, who's on the bottom, none of that. All we care about is we want to create a fraction that when we clean it up and take its limit, it's going to be a number. Okay? So, limit as n approaches infinity, big parentheses. Which one should I put on top based on what I told you a minute ago? 1 over the square root of n. The simpler one goes on top. 1 over the square root of n, then your fraction bar, and then the other one, 1 over 4 plus the square root of n equals.
So can't we just automatically assume that it's always going to be the bottom over the top one?
Yes, but you need to show the step, that you're doing a ratio.
Oh, yeah, but we don't
Yes.
have to like, show that.
No, you don't have to show it flipping up. As long as you know that this is going to come out to be the limit as n approaches infinity of 4 plus the square root of n over the square root of n. Now, things do change if your numerators are not 1s, because eventually there will be some problems where the numerator is not a 1. And that way you're going to have to do a little bit more. So in this case, yeah, you can just say the denominator of the bottom is going to be the top, for sure. Okay? Can I break that into 2 separate fractions? Yes. So that's going to be the limit as n approaches infinity of 4 over the square root of n plus what? 1. As I plug infinity into the square root on the bottom, it's going to become close to 0. So this is going to 0. So my limit is 1 again. Because I got a number answer, I can therefore say that A of n converges by the limit comparison test. Questions? Yes, sir.
Could you explain one more time why we cancel out the 4 over square root of n again?
Because when you plug an infinitely large number into the denominator, a million, a billion, a trillion, each of those fractions is getting closer and closer to 0. Even if you're taking the square root, it's still getting close to 0. So the limit is 0, the bigger your denominator goes.
So even I just always wondered the square root of infinity.
It's still infinity. It's still infinitely large. Yes, even though square roots tend to make things a little bit smaller, it's still infinitely large. Okay? All right, let's skip number 5 and move down to the bottom of the page at number 6. Now, you're going to have to figure out which series to compare the ones to. Now, since I'm not doing 5, I'm going to use this area to write down the 4 that they're the main choices. So down in this area, let's write them down. 1 over n was one of them, and it diverged. Can you see what I'm writing? Nope. So in this area right here, write 1 over n, and it diverges. 1 over n squared, and it converges. 1 over the square root of n, and it diverges. And a times r to the n, which converges also. So these are our basic choices. You can change the exponent on n for the p-series ones to be whatever you want. If n squared doesn't work, you could use n to the 6th if you wanted to. But the point is, you're choosing an exponent that's bigger than 1 here and smaller than 1 here. Okay? So let's take a look at number 6. We have the summation from 1 to infinity of 1 over 3n cubed minus 5n plus 7. Okay? Now, when we're dealing with polynomials, when these are polynomials up here, we want the exponents on top and bottom to be the same, because that way when we divide it into separate fractions, we're going to get a constant. That's the point. We like to get constants because then a constant means you're going to get a number answer. So I'm going to compare this one to 1 over n cubed, not 1 over n squared. I want the same exponent as the bottom. And this one converges. You must write down what you're comparing to and whether it converges or diverges in order to use this test. Okay? I'm going to call the first one a of n, and I'm going to call the other one b of n. Yes?
Is it converges because of the third power?
Because of the third power. If the power is bigger than 1, it's going to converge. Okay? So that one is going to converge. So now we're going to go ahead and set up our limit. Limit n approaches infinity, big parentheses. Now, once again, which one do we put on the top?
B.
The b of n, the simple one. 1 over n to the third on top over 1 over 3n cubed minus 5n plus 7 equals. Okay. Limit n approaches infinity, flip it up, clean it up. So that means it'd be 3n cubed minus 5n plus 7 over n to the third. We want the simplest single term on the bottom. We want the exponents top and bottom, the first term to be the same. That's why we chose n to the third. Because now when I break it into separate fractions, I'm going to get a constant. And that's what I want. So this equals the limit as n approaches infinity of 3n to the third over n to the third is 3 minus 5n over n to the third is going to be 5 over n squared, and then 7 over n to the third for the last term. Now, does everybody understand where all that came from? Broke it into separate fractions. So the two fractions after the 3, as I plug in infinitely large numbers, those two fractions are going to what? 0. So this is going to 0, this is going to 0, therefore the limit is 3. I got a constant limit, that's what I want. Now, because b of n converged, I can therefore say that a of n also converges. I think I want to start adding the word also converges by the limit comparison test. I didn't say also before, but the more I think about it, that shows that because I know b of n converges, a of n also converges. Okay? Number 7. Anybody got a guess as to what we ought to compare 7 to? 1 over square root of n. Now, when I did this problem by myself, I compared it to something different. And I thought, oh, we can make adjustments later. But then I found out, you know what? Their answer, this was first period, came up with 1 over square root of n also. It worked just as well as mine did. So it doesn't mean you always have to use the same thing. It helps if they're similar, but they don't have to be exactly the same. So I'm going to compare to 1 over the square root of n. And what does that one do? Converge or diverge? It diverges. And you must write that down, which diverges. And this one is my b of n. My original problem is a of n. Doesn't have to be that way. I think I'm going to stay consistent and just do that every time. A of n is the original, b of n is the one I'm comparing it to. Yes, sir?
So on the AP test, do we have to remember the comparison series?
Yes. You must memorize that. You must know when p series converge and diverge. All the stuff we've been putting in the flip chart, you got to know that. It's a lot to memorize, I know. But the more we practice with it, especially when we come to the review day, it's going to all start coming together and start clicking. Okay? So, limit as n approaches infinity. Do you think you could do this one yourself? Yes, why don't you give it a try? Put the correct one on top, clean it up, and see what you can do. Where do we go from here? And I had a feeling some of you might get to here and go, wait a minute, I don't know what to do next. That's okay. Now, listen to my question for just a minute. Is the square root of 1 over the square root of 4 the same thing as the square root of 1 over 4?
Yes.
No.
No, I mean, yeah.
Yeah, square root of 1 over 4?
Let me do it this
It
way.
would be the square root of one.
Pull this aside. Is the square root of 1 over the square root of 4 the same thing as the square root of 1 over 4?
Yes.
Are they the same? Yes. So where do you think I'm going with this?
Put a square root over the whole bracket.
Yes, I need to put a square root of the whole thing. So this is the limit as n approaches infinity of a big square root of 4n minus 2 over n. Now can you go from there? What do you think?
Yeah.
Can you break it into 2 separate fractions?
Oh, yeah.
Yes.
So limit as n approaches infinity. 4n over n reduces to what? Just to 4 minus 2 over n. All still in the radical, which is okay. The 2 over n, when you put an infinitely large number in for n, that's going to approach 0. So I'm going to have as my answer the square root of 4. DJ, question?
I did the other step, and I ended up with 2 minus square root of 2 over square root of n. It's not basically the same thing.
Okay, you cannot separate, you cannot pull these terms out individually when you're adding and subtracting, only when you're multiplying and dividing. So the 4n minus 2 in a radical is not the same thing as 2 square roots of n minus square root of 2. You can't do that mathematically, okay? So, therefore, a of n also what? Converges or diverges?
Diverges.
What did the original one do again? Diverges. So it also diverges by the limit comparison test.
So,
Yes.
I think about it. B of n, that's on top, right, in this problem?
In this problem it is.
So since it diverges, doesn't that mean that the bottom A of n can do anything?
Okay, we're not doing direct comparison, we're doing limit comparison.
Oh, okay.
Yeah, you're getting the two confused, and I understand. All that matters is if you get a limit, they're both going to do the same thing. It doesn't matter who's on top.
So it doesn't matter.
It doesn't matter for this test who's on top. We don't even look at that. All we look at is can we make a limit that comes out to a number.
So if the limit comes out to a number, they do the same thing.
Yes. If the limit comes out to a number, they do the same thing. That's the simplest explanation of the limit comparison test. Yes.
Even though we use limits in both?
Yes. We know, actually we didn't do a limit in the direct comparison. This whole page is limit
the whole
comparison.
page was-
Go back to
oh,
the
yeah.
previous page, that's direct. Okay? All right. Last period I did number 8, but I want to do number 9 instead. Okay, we're going to skip number 8 because how to do 8 is going to be talked about in 9. Okay. Until I teach this, you're going to have no idea what to compare this thing to. That number 9 series is a mess. It's got so much stuff in it that it's just a mess. So when you do the comparison, you can do not only the 4 that I told you, but you can do a combination of those. Okay? But you're going to have to figure out whether it converges or diverges. So, I have, forget about the 2 to the n for a minute. Look at the top, look at the bottom. How many more n's would I need to make them have the same number, top and bottom?
2.
I would need 2 more. So, I would need an n squared. Now, hold on just a minute. Make sure I do this right. I would need an n squared. It would need like a 1 over n squared to make the top turn into the right one. Okay? Because when I flip this, it'll end up on top with the n. Do you agree with me? Okay? Now, yuck, 2 to the n. I would just like very nicely for that thing to go away. I would just like it to go away. So if I put a 2 to the n up there, once I flip it, they'll cancel and it'll go away. Okay? So I'm going to compare it to this. Okay? Now the question is, what does this thing do? Converge or diverge? Okay, let's write a few terms out to see. When you plug in a 1, you're going to get 2 over 1, right? When you plug in a 2, you're going to get 4 over 4. When you plug in a 3, you're going to get 8 over 9. And then 2 over 4 is 16 over 16. Now it's kind of hard to tell who's winning. It's not really oscillating. It's eventually going to start going in one direction. My question is, who's growing faster? What's 2 to the 5th? 32. What's 5 squared? 25. Okay, now top is bigger than bottom, agreed? On the next one, will top be bigger than bottom? Top's going to be 64, bottom's only going to be 36.
So it diverges.
It is going to diverge. The top is bigger than the bottom, so the fractions are going to be top heavy, which means it's going to diverge. Exponentials grow faster than quadratics do. The top is an exponential, the bottom is a quadratic. So it is going to diverge, yes.
I also noticed like a pattern. I don't know if this would indicate that it diverged too, but like the top would be bigger and then they would be equal, and then the top would be smaller and then they'd be equal, and then top would be bigger. And then
Okay.
So I'm assuming they'd be equal.
No, they're not going to be equal anymore. It kind of does some weird stuff at the beginning because of the fact that it's both 2's, but after that it continues where the top just explodes big and the bottom grows, but not as fast. Yeah. The first 4 terms just kind of give a pattern, but they don't stay that way. After this, the top's going to explode and the bottom's going to grow, but not quite as fast. Okay? So, watch how this one works. We're going to do limit n approaches infinity of, now who's the ugly one? The ugly one's this one. This is the simple one. So in this case, we do want the 2 to the n. Oh, I forgot to label them. This is a of n, this is b of n. I want 2 to the n over n squared over the other one, n 2 to the n over 4n cubed plus 3. Now, let's pretend for a minute that you put them into the fraction, and when you clean it all up and all is said and done, it doesn't break into separate fractions. It's upside down. We'll just go back and fix it. Just switch your 2 fractions if something happens like that. Okay. Now, remember that the bottom is going to the top now. So this is limit n approaches infinity. I'm going to have 2 to the n and 4n squared plus 3 on top. And then I'm going to have these 2 right here, which is n to the 3rd times 2 to the n on the bottom. Now what's going to happen to the 2 to the n's? They cancel. Thank you. Go away. I don't like you. And now I have something I can break into separate fractions, don't I? So this is going to be the limit as n approaches infinity of, oops, I wrote that as squared and it's cubed, 4 plus 3 over n cubed. And that limit is 4. It is 4. Therefore, a of n also diverges, oops, almost wrote converges, diverges by the limit comparison test. And people who are watching me write going, it says right there you can't post this on the internet and you're putting this on YouTube. Yes, I can. I got permission from the author. I have permission from the author to do this. Don't report me. He knows. Okay. Questions? Do you think you could do these by yourself? That's kind of a hard one. The rest of them are pretty straightforward. Okay? But before I let you go, I'm going to answer a question. Yes?
Okay, so I'm kind of confusing myself. So basically with this, depending on what a of n does, or b of n, whatever that does, if you get the same answer, then the other function will do the same thing?
Okay. You are 90% correct. They will do the same thing as long as the ratio of the limits comes out to a number. It's not necessarily a same thing. It has to come out to a number. If it comes out to a number, then they do the same thing.
Okay, because I was confused as to like why I said diverge when it was a number, but then I realized you have to get a number for it to do what the other one.
Yes, exactly. You can have divergence in a number answer. Yes.
Could it come out as 0?
Yes, as long as it is a number. As long as it is a number. Usually it's not 0, it's usually something other than 0.
A number over infinity. Except we do that in mathematics, or-
Let me research that one. I'm not really sure. In other words, could everything come out to be 0? Could everything come out to be a constant? Chances are I don't think so. I'd have to go see if there is a possibility, but I don't think that ever happens. Okay? Anything else about questions? Yes, ma'am.
When you were doing like the 2n over 2 to the n over n squared,
Uh-huh.
I was looking at the little ones that says that converges and diverges.
Uh-huh.
How come can't you do like a times r n as the numerator and then like the 1n squared for the denominator, since it's n to a power? Because that has the a times r n.
Yes.
in the numerator.
It does. And that does work for this problem, if it was in the denominator. The only thing is, what's better than making it into one of the other ones is to get rid of it. And my goal was to get rid of it, so that's why I went ahead and went the route that I did. I can't use the AR to the n for this one, I just realized, because my R is 2, and R has to be less than 1. So I can't use it in this instance. I have to get rid of it. Okay? Y'all are asking great questions. Anybody else? Okay, do me a favor, get your flip chart. We are going to add something to it really quickly. Turn it open to the page that we just glued in, which is comparison tests. Now, I'm only going to write it on the bottom, on the limit one, but it is applicable to the top and the bottom. I want to write down those 4 benchmarks right here in this, so when you open it up to use it, you can see what the 4 functions are that you want to start comparing to. So, I'm going to write 1 over n, and it diverges, 1 over n squared, and it converges, 1 over the square root of n, and it diverges, and a times r to the n, I wrote it wrong, darn it, r to the n, boy, I messed it up, makes me mad, a times r to the n, and it converges, as long as 0 is less than r is less than 1. Yes, sir.
You can use any function that we know converges or diverges.
Yes, you can use anything. You can. These are the most commonly used ones. That's why we list them. Okay? So these are our comparisons. These are what I call the b to the n's. I've started getting in the habit of a to the n is the problem, b to the n is what I'm comparing it to. It's whatever you want to do. You don't have to do it that way, but you can if you want to. All right? Any other questions? Great.